Hello all, and welcome to the second equipment review video from Surface Ventures. I'm Dr. Sam McMaster, Content Manager at Surface Ventures, and I'm once again at Micromaterials in Wrexham to further explore the NanoTest Vantage located behind me. Today, we will be exploring one of the additional modules of the NanoTest Vantage platform, specifically the Impact module. The Impact module can be utilized at either the nano or micro scale, depending on the load head utilized. This testing mode can be used under ambient conditions, in controlled atmospheres, and at elevated temperatures. Today, we will explore the fundamentals of small-scale impact testing, look at the equipment in more detail, explain how it differs from nano-indentation setup, show how impact testing is set up, and how data is analyzed. Nano impact testing is used for high strain rate contact testing. The strain rates of nano impact testing are typically 100 to 1000 per second or higher, many orders of magnitude greater than the nano indentation strain rates of 0.0001 to 0.01 per second. Nano impact can be used to compare the toughness and fatigue fracture resistance of thin films and coatings. Critically, the test can deliver high impact energy concentrated into a tiny near-surface sample volume, making it highly sensitive to coating properties. As such, it can be used for assessing the durability of high-speed machining tools, to evaluate the erosion resistance of aero engine thermal barrier coatings, and diamond-like carbon coatings for highly loaded automotive components such as valve train components. Impact testing differs from nano-indentation testing in that either a spherical or cube corner indenter is typically used as opposed to the common Berkovich indenter. Using the cube corner indenter allows for failure of a coating system to be driven more quickly, whereas a spherical indenter allows for fatigue resistance to be studied. As with nano-indentation, diamond is generally employed as the indenter material due to its high hardness and elastic modulus. The parameters can be varied for impact testing are probe geometry, accelerating distance, accelerating force, impact angle, number of cycles, and impact frequency. As covered in the previous video, the NanoTest Vantage platform has some key design differences from other indentation units that allow it to operate as a multifunction test platform without compromising its nano-indentation capabilities. Instead of being a top-down indenter, as many other platforms are, it's a horizontally loading pendulum system. It is this pendulum-based design that allows the high energy delivery that's key to impact testing. The nano loading head, seen here at the front, can achieve static impact loads of 100 millinewtons and 5 newtons with a micro loading head at the rear. The final impact force will be higher and depends on other parameters such as the accelerating distance, which can be up to 24 microns for nano impact and 70 microns for micro impact. This high energy density accelerated fatigue test is capable of fracturing all types of hard, wear resistant coatings up to around 5 microns in thickness. The optical microscope, seen at the very rear of the system, can be used to look at specific areas on the sample to test with a repositioning accuracy of better than 0.5 microns. The micro and nano impact modules can be used to predict coating performance under erosive conditions and also can mimic the repetitive contact in end milling. This platform was used during my PhD studies to characterize DLC coatings with nanomechanics to inform on their tribological performance. I specifically used the micro and nano impact modules to explore the fatigue resistance of DLC coatings and relate erosive wear performance as characterized by optical analysis. As mentioned before, this platform is extremely versatile and able to cater for multiple industries, applications, and different testing regimes. With the addition of an environmental chamber, reduced oxygen or purge gas conditions can be established for testing at non-ambient temperatures. Temperatures of up to 850 degrees Celsius can be achieved for impact testing as well as nano-indentation and scratch testing. The initial setup of an impact test is quite similar to an indentation test in terms of sample mounting. First, we set up the electromagnet here at the bottom to be the correct distance away from the load head in order to achieve a consistent acceleration distance and therefore impact energy for each test. Now we can install the sample using the standard sample stub for the NanoTest platform. Here we can see multiple samples installed. As I said earlier, you can test multiple samples at once, and in the platform itself we have the sample that we're going to test. So let's now move to the computer where you can see the software setup. Now we can set up our test. So for this, we go to Experiment, Impact. We can either define a new schedule or, as we will do now, import a schedule that has already been defined. I'm going to click Import, Load. We are at the initial position, so we're going to click Initial Position Located. So we've selected the Multiple Impulse option, or Impact, in this case. Now we can input or have inputted the key parameters such as impact load. In this case, we have 80 millinewtons, and this is the normal force applied through the load head. The impulse height, also referred to as the acceleration distance, the impulse height here as 15,000 nanometers or 15 microns, and the impact frequency. Okay, so we can see this just here under pulse control. It's 2 seconds on and 2 seconds off, which gives us 1 impact every 4 seconds. We also need to input the total test time. This is typically on the order of 1 to 10 minutes. In this case, we have 4 minutes set. We can repeat the test any number of times by inputting the appropriate number of rows and columns. For this demonstration, we just have 1 impact used. And now we can click OK, finished. And now we've seen how a test is set up, and we will now allow the impact sequence to finish before we can review the data. So we've now finished our nano impact test on our titanium nitride coated silicon, and we're going to analyze the data. So to do this, we go to Analysis, Impact, Review Data File, select the relevant one, in which case it was our 80 millinewton load with 15 micron retraction distance. Load. So the raw data outputted by an impact test is much simpler than nano indentation, as we're just monitoring the evolution of depth with respect to time. As we open the impact data file, you can see the graph of depth versus time here. You'll notice that we have a large amount of negative depth data. This is the recording depth from the indenter withdrawing from the sample before an impact. We have a couple of options to process this negative depth data out of the dataset. By clicking on Options, we can either remove the data on the backstop or remove the spikes and data on the backstop. So we're going to select this option now. As you can see, that's changed quite dramatically. When the indenter impacts a sample, there's the primary impact, but also the successive smaller impacts as energy is lost from the system. Removing spikes will smooth out these smaller impacts out of the data. We can have a look through the depth time of each impact. Depth of time data can be exported here. Various options, and this is available in standard formats such as tab separated text files to allow the user to plot the data in a program of their choice. So as you can see on our titanium nitride coating, we have an initial depth here of just over 3.7 microns. We are then getting deeper and deeper into the coating system until we have our dramatic failure. So you can see here is this reduction in depth is likely some debris sitting in the impact site, and we can then see a much more rapid increase in depth as we've broken through the coating with our sharp cube quarter indenter, and we are now impacting into the substrate. Okay, now we've seen a typical repetitive impact test, we will explore the randomized impact test method. The randomized impact test allows a program number of impacts to be distributed within a specified region of the sample in order to directly study how damage from one impact affects subsequent damage. This allows for simulation of impacts in a methodology more similar to erosion, where particle impacts impart energy across an area. The technique is particularly well suited for studying damage mechanisms on thermal barrier coatings and exhibits good correlation to erosion tests, both in terms of damage mechanism and wear rate. So, as before, we're going to go to Experiment, Impact. We've already set up a schedule for this. I'm going to click Import Schedule, Random Impact Schedule, and Load. So for information, we're using a different indenter to before. Previously, we had a cube corner, but now we have a 25 micron radius sphericonical indenter, and our sample is magnesia stabilized zirconia. We're already positioned on the microloading head, ready to go. So we're going to click Initial Position Located. We have selected dynamic hardness as we are performing multiple single impacts with changing position. Okay. We have an impulse load of 1000 millinewtons or 1 newton, an impulse height of 50 microns. Okay. Same total sampling time as before, 50 impacts. And to set up our area, we have impulse point offset, user entered, edit offsets, and then we would set the plus and minus displacement between Y and Z. Okay, so we're going to click OK on that. And now that this is all set up, we're going to click OK, finished, and then we can run our test. Okay, so now the best way to analyze your randomized impact is by microscopy. So we have here our micrograph of the impact area. So as we can see, there is extensive damage. This was caused by 50 microns on a 125 by 125 micron area. Here's another example of two multi-layered nitride coatings, which illustrates the sensitivity of this test to coating performance under high strain rate impact across a defined area. The two samples were subjected to 50 1 Newton impacts across a 400 by 400 micrometer area. Extensive coating failure is observed for coating B, in contrast to coating A, which does not show any failure, despite both coatings having very similar hardness and elastic modulus. Impact testing is a powerful tool to accompany nanoindentation to characterize thin films and coatings at very high strain rates and energy densities. As with nanoindentation, care must be taken with test setup, but analysis of the data allows for comparison between different coating systems. The software provides a simple interface to explore the generated data. In addition to fixed impact grids, you're also able to perform statistical distributions over a predefined area to more accurately mimic erosive wear conditions. You can find out more about equipment capabilities with the provided links to Micromaterials technical notes in the description below. Thank you all for watching this equipment review from Surface Ventures. We hope you enjoyed this video. Thanks to Micromaterials for allowing us to film here today. We hope this was a useful insight into the impact testing with the NanoTest Vantage. Best of luck with your impact experiments.